Good morning students. In this video we can discuss about addresses in the target code. So in this session we discuss how the names in IR representation, that is intermediate representation. So whatever the names we are used in intermediate representation, so that names can be converted into addresses. So these converted addresses can be used in the target code. So by simply we can observe how whatever the names are used in 3 address code representation, so that names can be how such names can be converted into addresses in target code. So here we can observe the simple code generation of the target code generation of the simple procedures. So we can consider some simple procedure calls and return so we consider simple procedure calls and returns, those procedure call returns, and here we are using the some static and stack allocation to store such information. So already we was discussed in last session, that is runtime environment. So in that session we was discussed, so whatever the program executed by the compiler, so each and every program is executes with their own local data or with their own local address space or logical address space. It's by using their own logical address space. So that logical address space is partitioned into 4 parts or 4 data areas. Those are a statically determined area code. So first one is the statically determined area code and the second one is the statically determined data area, and third one is the dynamically managed area, and final one is the dynamically managed area for stack. So here coming to the first one, a statically determined area code. So this area code is used for holding the executable target code. So here whatever the target code was we are used to executing the particular program, such code was holded or stored in this statically determined area code. So here the size of the target code, so whatever the target code requires, how much amount of memory can be required to complete that particular target code, so that information can be fixed or decided at the time of compilation time only. So that's why we says that is statically determined area code. So such area code was used for execution of that particular program. So second one is a statically determined data area. So this data area is used for storing the activation record information. So already we discussed in last runtime environment concept. So here what is meant by activation record, so how to store activation records. So here generally we prefer to storing the activation records, we can prefer the stack data or stack data structure. So by using the stack data structure we can store such information. So here additional to the activation records we are also stores whatever the global constants are used to generate that particular target code by the compiler. So here the size of the such global constants and the compiler data, so that data can be data or memory size can be fixed. So why? Because these all things can be generated or calculated at the time of compilation. So that's why these all are the static. So coming to the third one, so a dynamically managed area for heap. So here we are using dynamically managed area by using the heap data structure or heap storage. So here already we discussed what is meant by heap allocation or heap management. So here actually heap is used for storing or holding the data objects. So such data objects are allocated and freed. So that means allocating some memory location, and after completion of that particular execution, that particular memory location can be leaved or terminated for that particular variable. So by simply allocated and free up that particular allocations of the variables during the program execution time, at the time of program execution. And here the size of the heap cannot be determined at the time of compilation. Why? Because this heap storage is determined or calculated specified at the time of execution or runtime. So that's why. So and final one is a dynamically managed area. Here to maintain such dynamically managed area with the help of stack information or stack storage. So this stack is used for holding the activation records, and such activation records are created at the time created and destroyed. So that means such activation records are creating and removing at the time of execution time or at the time of runtime. So here the size of this stack allocation or stack is also cannot be determined at the time of compilation. So these are the 4 data areas to performing the each and every program execution. So now we consider some simple example and check how to performing the static allocation or stack allocation for the target code. So now we consider some static allocation. So here to illustrate or to know about how to generating the code generation or code generator, so we are using some simple procedure calls. So to generate code generation for such simple procedure calls, we are using some 3 address code representations or some 3 address code statements. Those are call, callee, return, halt, action. So these are the 4 statements or 3 address code statements was used to generate target code for simple procedure calls and their return statements. So here the size and layout of activation records are, so whatever the size and whatever the layout of that particular memory or that particular records, so such are determined by the code generator. So these 2 things can be determined by the code generator. So here code generator is used to determine or to know how much amount of size or how much amount of memory or how many what is the layout of that particular memory. Such details can be determined or such details can be provided by the code generator. So with the help of whatever the information available in symbol table, so that means whatever the variable names was used to store such particular simple procedure calls and their returns information in the symbol table, based on that information, so it can allocates the some memory space and then layout of the memory. So these things can be implemented by the target code generator or code generator. So first of all, we illustrate how to store returned address. So that means some return address, so in an activation record on a procedure call, and also how to return control to it after the procedure call. So that means here first of all we know while we will go for knowing how to store and how to providing the size and layout of any simple procedure calls. So in this purpose, first of all we know how to store some returned value in activation record. That means here return value means some function can return some value or some address. So that information can be stored, how we can store into activation record, and also we can discuss about how we can return control to the called procedure. So for our convenience, we assume the first location of the activation record is holds the whatever the return address. So in this process, so first location of the activation record or stack we are using to store whatever the return address of the function. So such a return address can be stored at the beginning of the activation record. So now we consider some simple statement, a simplest case. So in this case can allocate the some static allocation. So by using this simplest case, we are using the static allocation. How we can store and return the procedure calls. So for that purpose, we are using the 2 instructions or 2 target machine instructions. Those are st space callee dot static area ash here plus 20. So here ash here plus 20 means ash indicates here we are storing some address information, or here we are storing some address value, and plus 20 indicates so this heap memory size or this memory size, that means it requires minimum 20 bytes of memory. So for that purpose here we mention ash here plus 20, and next instruction is br space callee dot code area. So these are the 2 instructions was used to generate the target machine code. So here st means store instruction. Here st instruction indicates store instruction. That means it saves some return address at beginning of the activation record. So here whatever the address was written by the callee function, that written address can be stored in the at the beginning of the activation record. So this value can be used for callee function, whatever the function was called callee. So that function was used this returned address, and here BR instruction, branch instruction, so it can transfer control to the target code. So this branch instruction is used to transfer the control to the target code for the called procedure call. So that means here whenever, for example, there are two procedures P and Q. Whenever procedure P was calling procedure Q, so in this process, first of all, procedure Q returns some address, whatever the value written by the procedure Q, that value was stored in some address, that address was returned to the procedure P. So now after returning that particular, first of all, that return address can be stored into at the beginning of the activation record, and then that control can be transferred to the called procedure. Here called procedure is P and callee procedure is Q. So here first of all, whatever the callee function return address, whatever the address was written by the callee function, that is Q function returned address, that address is stored at the beginning of the activation record. After returning that particular address, with the help of this branching statement or branch statement, so we can transfer the control on that particular address. So whatever the address was written by the callee function, so that particular address control information can be passed to the called procedure P. So this is the process. So here why we are using callee.static area attribute and why we are using callee.code area attribute. So here callee.static area, this attribute is a constant, callee.static area. So this attribute returns some constant. So that constant contains whatever the address was given by the callee function at beginning of the activation record. So at the same way, this callee.code area, so callee.code area, so this is also some attribute. This attribute is also constant, which refers to the address of the first instruction of called procedure. So here callee.static area is this object is used for callee function, and callee.code area, so this attribute is also constant. So this constant is used for called procedure. So here in our assumption P and Q, so this address is used by procedure P and Q, and this address is used by procedure P. Why? Because here procedure Q is a callee function, callee procedure, and procedure P is a called procedure. So just already we discussed what is meant by hash here plus 20, so which instructs the some address, return address, and which requires the heap storage of minimum 20 bytes. So it requires either 20 bytes or 5 words. So after completion of this one, so the code for a procedure, so that means whatever the return address, and then whatever the return address, that address was handed over to the called procedure, and then after completion of the entire body of the function, so finally it returns calling procedure. So it's finally that instruction is going to the halt state, that means which can terminate the which can terminate that execution or transferring the control to the operating system. That control of execution, program execution can be transferred to the operating system. For that purpose we are using the halt state. So here we are using some return statement, so some return address. So that return address of callee statement can be implemented by a simple jump instruction. So that is like as br space star callee.static area. So with the help of this type of jump statements, we can return whatever the callee statement address, that address can be returned to the called procedure. So these are the details about how to performing the static allocation. So now we discuss how to what is meant by stack allocation. Here actually whatever the concept or whatever the code generator was used the static allocation, so that static allocation can become stack allocation. So by using the relative addresses for storage in activation record. So here first of all we know what is meant by relative address, and then what is meant by immediate indexed address. So here indexed address mode means, so here we are using or storing the some values, such values are addresses. So such values as addresses. That means we are using some registers to store some information. So that information is related to the address of some another block or some procedure or some variable or some object. At the same way here relative address. So here relative addresses means so which was used to just mention or just indicate beginning of the that particular activation record. So that means that particular stack or that particular procedure can be having some number of memory locations or some array of information. So out of those array locations or some number of memory locations, what are the beginning position of the memory locations. So such memory locations can be implemented with the help used with the help of relative addresses. That just it can indicate the just beginning of the that particular activation record or that particular memory location. So for that purpose we are using the relative addresses for returning the addresses as a parameters or as a values. For that purpose we are using the indexed addresses. So here in stack allocation we are using the relative addresses. Already we discussed in runtime runtime environment. We was discussed what is meant by activation record, how to store activation records and nested depths. In that session we was discussed about what is meant by activation record, what are the several options in the activation records. At the same way here we are using the stack allocation can be implemented with the help of some which can define just beginning of the that particular activation record location. So for that purpose we are using some relative addresses. So based on this address, whenever we are storing or we are invoking another procedure, then it can enter it into the subchild or next entry of the memory location. In this manner stack pointer can be increased. For example, we shall use some positive offsets by maintaining in a register SP. Here SP indicates stack pointer. So here SP is a pointer to the beginning of the activation record on top of the stack. So here SP indicates the beginning of the some pointer. That pointer can indicate activation record of the that particular stack. So for that purpose we are using the relative addresses. So in this process, whenever a procedure call occurs, the calling procedure increments SP pointer value and returns control to the called procedure. For example, initially here SP pointer is at a 0th location, just value is either 0. Whenever some procedure call occurs, then SP pointer will be incremented to the next position, either one position, first position. So and then whatever the value stored in first position, that information can be hand over to the called procedure. So this is the process of stack allocation. And finally we discuss about runtime addresses for names. So till now we are discussing how to generating the names for IR representation of the code. So now we discuss how we can providing the runtime environment for that particular names. So here the storage allocation strategy and layout of local data in an activation record for a procedure call is nothing but names for the that particular storage, whatever the names was required to store such information in memory access or in memory. So here we assume that a name in a 3 address statement is really a pointer. So that means here name means some pointer. So that pointer is reference to the symbol table entry. So whatever the name in the symbol table, so that entry can be referenced by the some pointer. So for that pointer is indicates some reference to the that particular name on symbol table entry. So already in previous concept just now we discussed. So here yeah, so the size and layout of activation records are determined by the code generator with the help of whatever the information about names stored in the symbol table. So at the same way, so here while we will go for accessing the runtime environment for names, at the time here it provides the just some reference to the that particular symbol table entry. So here this approach is a significant some better advantage. So that is nothing but, so it makes the compiler is more portable. So why? Because in case the front end of the compiler is changed from one system to another system, still we can easily execute the particular code from one machine to another machine without any drawbacks or any failures. So at the same way here, generating the specific sequence of access steps while generating intermediate code can be significant advantage. So that is that advantage is an optimizing compiler. So why? Because the optimizer can take the advantage of the details, whatever the details was provided by the symbol table and then this runtime environment. So based on such details, so it can easily accessing those three address statements. So these are the details about what is meant by addresses in the target code and how to create the names for intermediate representation of the code. Thank you.